Today we're going to take a look at the graphs of rational functions. First, let's remind ourselves what a rational function is. A rational function is when you have two polynomials that are divided. So you're going to look just like a kind of a fancy fraction where the top and the bottom are both polynomials. An example of that would be this one. Now, one thing that we need to ask ourselves on these is, what's the domain going to be? Because that's going to tell us a little bit about what our graph might actually look like. So first thing you should notice is we have a fraction and you can't divide by 0. So the denominator cannot be 0 in these. So take a moment and pause and set the denominator equal to 0 and find the two values that are going to come up that we cannot have plugged into this formula because it will make the denominator 0. Now that you've had a chance to do that, you should have noticed that x squared plus 3x minus 4 cannot be 0. So if you factored this, two things that multiply to get negative 4 and add up to 3 are positive 4 and negative 1. So this factors into x plus 4 times x minus 1. So that cannot equal 0. If that's going to be 0, then either the x plus 4 would be 0 or the x minus 1 would be 0. So if you go ahead and solve to find out what x plus 4, if that cannot be 0, what x cannot be, you would subtract 4 from both sides and find out that x cannot be negative 4. If you do the same thing with the other factor, you would find out that x minus 1 cannot be 0. So if you add 1 to both sides, x cannot be 1. Remember that we do need to write this in formal notation. You'll either be asked for set builder notation or interval notation. For set builder notation, it would be the set of all x such that x cannot equal negative 4, and then you can either use the word or a comma, and x cannot equal 1, because we're assuming that we're in the real numbers. If you're doing interval notation, the lower value for this is negative 4. So if you're going from left to right across your x-axis, you would come up from negative infinity, and the first thing you would hit that you cannot be is negative 4. So we would stop at negative 4 with a round bracket because we're not going to touch it. And then there's going to be a union symbol, and then you're going to go from negative 4 to 1 because you can't touch 1, so you have to stop at 1 with a round bracket. Everything's going to be a round bracket in this. And then after 1 you can continue on. So you'll use a union symbol and then you'll go from 1 off into positive infinity. Kind of ran out of room there. So that's what our domain is going to be. Now, it would be interesting to see what that does to our graph. If x can't be negative 4 or 1, what's that going to do to your graph? So think about that for a minute, and then I'd like you to go to Desmos and graph this. Now remember, when you put it into Desmos, you're going to need to have parentheses around the top. When you do your division symbol, it'll automatically stick a fraction in there, and you can continue to put the denominator in. So go ahead and take a moment to do that and see what happens, and then we'll discuss it. So you can pause now and try that. And you can either do that at desmos.com or you can do it with the app on your phone from Desmos. So let's take a look at what you saw. On this graph, you'll see that over here at negative 4, that you have this line here, this invisible line that seems to go straight up and down. That's a line at x equals negative 4 that this graph actually never touches. It angles very close to it, but it never actually reaches it. That's called a vertical asymptote. It's an invisible line that we're actually going to put in as a dashed line when we graph these by hand to signify that we get really close to it, but we don't actually reach it. Notice that over here at 1, we can't touch 1 either. And 1 is, since our grid here is going up by halves, because 2 is right here and it took 4 squares to get there, that this spot right here is where 1 is. And so notice that it comes very close to 1, but it never touches it either. So you have things that happen in the middle of the graph and things that happen out on the sides, but it never actually touches those vertical asymptotes at x equals -4 and x equals 1. So that's actually kind of interesting. Let's see what happens with other graphs that are like this. So what I'd like you to do is for each of the following graphs, pause the video for a moment, take a look at them, set your denominators equal to 0, and see what the domain is going to be. What are the things that you cannot have and what are the things that you can have? And then go to Desmos and see what happens to those graphs. And the second one's going to have something different. So be careful with that one and talk with a partner about what happened on that second one. So go ahead and pause and do that for a moment. Now that you've had a chance to go ahead and do that, let's take a look at the graphs. You should have found on the first one that when you factored the denominator of that two things that would multiply to get -35 and add up to -2 would be a -7 and a +5. So the denominator of this factored into x minus 7 and x plus 5. That meant that once you set those equal to 0 and solved, that you found out that x could not be 7 and that x could not be -5. So when we look at the graph of that, notice that over here at -5, because that's a number that can't be plugged in, we have a vertical asymptote. Notice that over here at 7, which is another number we can't plug in, we also have a vertical asymptote. But that graph of r of x was a little bit interesting. The same thing didn't happen. When you factored the denominator, that was a difference of squares. And so that factored into x plus 3 times x minus 3. Take a moment to discuss whether you actually had asymptotes at both 3 and -3, because those would be the two values that you couldn't plug in. If we take a look at the graph now, notice that you only had one asymptote. The only asymptote we had was over here at 3. 3 could not be plugged in, and that showed up. But -3 was not supposed to be plugged in either. If you take a look at this rational expression with the denominator in factored form, notice that the numerator of this fraction also has an x plus 3. The -3 is what we call a removable restriction. It is a restriction on the original formula, but you can remove it because it cancels out with what's in the top. You do still have a 1 in the numerator, but the simplified form of this ends up being 1 over x minus 3. In this form, the only asymptote that shows up is at 3. What happens is at the -3 for the original graph, you actually have a little hole, which we will signify with an open dot on our graphs if that shows up. You don't actually see it when you graph it in Desmos or on a graphing calculator. It's very hard for them to actually show that hole, but there is a hole there at the point where x equals -3. So over on this side of your graph where x equals -3 right in there somewhere, you would have a actual hole or an open dot is what would end up happening there. So your vertical asymptotes you're going to find by taking the denominator of the fractions and setting them equal to 0 and seeing what is not okay to be plugged in. Now, let's take a look at some general forms of some basic graphs and see if we can figure out some interesting things for our graphs. What I would like you to do now is take a look at these 4 graphs. they're each very, very similar, but they have some slight differences. So I would like you to take, and in groups or with a partner, take and graph each of these in Desmos or a graphing calculator and see what happens, and see if you can explain what the differences are and why those differences happen. So go ahead and pause and try that. You can either use your Desmos app or a graphing calculator. Now that you've had a chance to do that, let's go ahead and take a look at the graphs. The first graph that you have for a of x, that's 1 over x. And if you'll remember a couple weeks ago, we talked about 1 over x as being the reciprocal function. And that function had a graph that I called a hyperbola. And so if we take a look at that graph, notice that you cannot plug 0 in the denominator, and that gives us a vertical asymptote at x equals 0 right here. And this one here doesn't have the negative like b of x did. And notice that our hyperbola shape shows up here in the first quadrant and down in the third quadrant. Now let's take a look at what happened when we stuck the negative in there. If you'll remember, a negative out front was a transformation that made it so that you reflected over the x-axis. Well, when we take a look at b of x with that negative in there, sure enough, you reflect over the x-axis. We still have our vertical asymptote at x equals 0. But now our hyperbola shape is in the second quadrant, and it's also in the fourth quadrant instead. Now, the other two had a square on the bottom. The square on the bottom, if you square a positive, you get a positive. If you square a negative, you get a positive. So if you want to imagine what would happen on our function c, everything gets squared in the denominator. The numerator is 1, which is already positive. So all your values have to be positive. So if you notice on the graph, that makes it so our hyperbola shape is above the x-axis. It's in quadrants 1 and quadrants 2. And we still can't plug in 0, so we still have our vertical asymptote here at x equals 0. When you stick a negative out in front, our transformation would take that and reflect it over the x-axis. So, as you guessed it, for part D, or function D, that takes and flips it down into quadrants 3 and 4. Now, knowing that those are the basic shapes and that we have transformations that can shift these shapes left, right, and up and down, take a look at these functions and try and sketch what you think it would be. So in your groups or tables, sketch what you think these would be based on what functions A, B, and C and D looked like, and then go to Desmos and check yourself to see if you're correct. So you can pause now and give that a try. Now, what you probably noticed is that on R of x is very similar to A of x. So all we have is this plus 2 here. So rather than having your vertical asymptote at x equals 0, this shifted to the left, and your vertical axis is now at x equals -2. Since this function is very similar to A of x, once you put that vertical axis in, and that along with your x-axis kind of divides things into quadrants, and your hyperbola shape should have shown up in the first quadrant type area that's getting divided and your third quadrant type area. So your sketch should have been similar to this, where you went over to -2, and your vertical asymptote, we can use dashed lines for that, was right here. We haven't talked about horizontal asymptotes yet, but there technically is a horizontal asymptote here at the x-axis, and those asymptotes have divided it into quadrants. So now you have your hyperbola shape up in this quadrant and down in this quadrant if we think of it as quadrants divided by those asymptotes. Similarly, on the h of x, that's similar to c. So you still had a vertical asymptote at -2, but now because it's squared, rather than having your hyperbola shape in the bottom, both of them ended up being in the top. Now, I want to compare these two. The first one, the x plus 2, technically, if you look at it, had an exponent of 1 on it. And notice that on this asymptote right here, that the hyperbola shape only had one thing going to it as you went to -infinity down here, and one thing going up to it as you went to +infinity there. If you look at h of x, I'll switch to green for that one. As you approached +infinity, the actual graph went up on both sides. What we call that is a multiplicity of 2 in these graphs. So if you remember, we talked about multiplicities for polynomials in the last class. For this particular one, multiplicity of 2 is going to mean that your graph approaches your asymptote from both sides. If your multiplicity is 1, as it is in R of x, you're going to have it only approach from one side as you're going to -infinity and one side as you're going to +infinity. So if you look at the bottom ones, the same kind of thing happened. The only thing that happened was we flipped over the x-axis. So if we look at j of x had an asymptote at 3. The x minus 3 down here took our asymptote that would have been at x equals 0 and shifted it to the right over to 3. So you can use a dashed line to signify that your asymptote has now moved here. So we now have an asymptote over here at 3, and then the x-axis also acts as an asymptote. Because it's negative, we have reflected over the x-axis, and rather than being in what would be quadrants 1 and 3, if we think of our asymptotes as dividing into quadrants, we're now in what would be 2 and 4. Notice that the denominator did not have the square, so your multiplicity is still 1. And notice as we go to -infinity for our range that we only approach that vertical asymptote on one side. As we go to +infinity for our range, we only approach this vertical asymptote from one side. The only difference that happened in g of x was that since the multiplicity is now 2 here and it's negative, we are now down in quadrants 3 and 4 if we think of our asymptotes as dividing into quadrants. And now we approach -infinity from both sides. That gives it that multiplicity of 2 down there. So now let's take a look at what if our horizontal asymptote is not necessarily 0. All